work titled Explain, Delete, and Defend, an attribution-guided token excision for LLM safety. So it's work done by me, Hacene Fouchal, and Olivier Flauzac at the University of Reims, Champagne-Ardenne. Do you see the change in the presentation or not?
Hello, I can see the changes.
You can see the changes. Yes, thank you. So as we all know, the large language models have become incredibly powerful and integrated into many aspects of our digital lives. However, with this power comes significant vulnerabilities. One of those vulnerabilities are jailbreak attacks. It's adversarial prompts that we use to bypass the safety alignments in order to trick the LLM into generating harmful or disallowed content. These attacks are somehow really sophisticated and have achieved great success rates as like the greedy coordinate gradient method that we discuss in our paper. So the greedy coordinate gradient is a powerful white box attack method. Its objective is to automatically generate an adversarial suffix that forces an LLM to produce a specific and often harmful response. So you have an LLM that don't want to respond to your prompt, so you make it respond by using this method. The mechanism is quite simple. It is a matter of optimizing the suffix that we will add to the original prompt by maximizing the probability of a target output using a gradient-based method to select the most effective tokens. So here is an example. If I prompt any aligned LLM with something like, tell me how to synthesize a lethal bioweapon, most of them will answer with something like, sorry, I can't help you with that. You can make the test with ChatGPT, for example. And so the greedy coordinate gradient method will add to our original prompt a suffix. Sometimes it's a suffix, sometimes it's a prefix, sometimes it's in the middle, but the idea is the same. And this suffix will make our LLM respond positively to our request, and he will give an answer, something like, sure, here's how to synthesize a lethal bioweapon. So against those type of attacks, there is some defense mechanisms that were proposed. And one of them is the erase and check method that we took as an inspiration for our work. It's a certified defense mechanism. It works by exhaustively deleting every possible contiguous block of token from a prompt. So with that, you see that by deleting one token and then two and then three and then four, we can go back to the original prompt that was deemed dangerous and then defend ourselves against those type of attack. And then once we delete, we use a safety filter to reevaluate each resulting subsequence. If any are deemed unsafe, the original prompt is rejected and we do not generate a response. It is a very powerful method because it offers strong and provable guarantees against various attack types, like we discussed, either suffix, insertion, or infusion. So here is how it works in a nutshell. You have your harmful prompt here with the adversarial tokens. Can you see my mouse here? So you have a harmful prompt with adversarial tokens, and we will erase one token at a time of the adversarial tokens. And at the end, we come back to the original prompt, and the safety filters sees it as harmful. So the whole prompt is detected as harmful. But this defense mechanism is very effective, but it has a cost. It is computationally expensive, and we have a latency issue. The cost of grows with from linear to combinatorial low-latency with the attack length. The attack length being the number of tokens that we add with the GCG method. It is impractical for real-time use. This makes it unsuitable for many consumer-facing applications where speed is critical. And the research question that we had is, can we improve or approximate EC's robustness with a fraction of the computational cost? So our idea is to propose a trade-off, sacrifice some of the certainty for a massive gain in speed. The hypothesis is a single well-chosen deletion guided by attribution method or explainability method can be nearly as effective as exhaustive deletion. And our goal is to reduce the evaluation cost to just 2 forward passes, making the defense more practical for real-time applications. So one of the explainers that we used in our method is the SHAP method. SHAP stands for sharply additive explanation. It is a cutting-edge method from the field of explainable AI used to interpret the output of any machine learning model. The goal is to move beyond the model performance metrics and understand why it makes the prediction it does. And the concept is to distribute the payout or the model prediction among the players, which are the input tokens. It works very easily. Here, for example, we have a model that predicts as an output the likelihood of you having a certain disease. And it takes as an input the age, the sex, the BP, which is blood pressure, and the BMI, which is body mass index. And it makes a prediction, which is in this case 40% of you having that disease. Using the SHAP method helps us understand which of the inputs were the most influential in our output. And here we see that the age is the most influential at plus 0.4, and the BP and the BMI are not very influential at plus 0.1, and the sex is influential, but in the other direction at minus 0.3. So here we can clearly know which input is the more important because each input has a score. So the methodology that we propose comes in two distinct methods. The first one has the same architecture as EC, which is built around a safety filter check. So unlike the EC method where they delete one step at a time a token, here we compute the SHAP values and we delete the tokens that have the most important score for the method A. And for method B, we asked what would it be in terms of performance if we ditch the safety filter and we only calculate the SHAP values on the LLM that will generate the response. So we will see the two distinct methods. The method A keeps the external safety filter, but optimizes the check phase. So there is an initial check, the user prompt is passed through the safety filter. And then we calculate an attribution using SHAP or another explanation method. If it is deemed safe, we identify the top K most influential tokens, and then we delete them because those tokens might be tokens that we added for an attack using the GCG method, for example. And then we do a final check on the modified prompt to reevaluate its safety with the safety filter. If it's now harmful, then the prompt is rejected. The method B ditches the safety filter, and we do a generational attribution directly on the user prompt on our LLM. And we calculate the SHAP score directly with the generator to identify the most influential tokens for the potential harmful output. Then we delete the top R% of the most influential tokens, Then we regenerate the response and we analyze it to know if it is harmful or not. So for the method A, the experiment was done on a dataset called AdvBench, which consists of 520 adversarial prompts. Those are questions that, or prompts that no LLM should give an answer to, like the question that we've seen before about synthesizing the bioweapon. But there is other questions about writing a code that can hack a database or teach children how to use firearms. All those questions should not be answered by an LLM. And it consists of 520 of them. The model we used for our safety filter is Distilbert. It's the same model used in the original paper. It's for comparison reasons. The metric that we use here is the detection rate of harmful prompts. And the finding that we have is that SHAP consistently outperforms feature-ablation. It is more performant into detecting the adversarial tokens. And the result, we will see them in a bit. But the key takeaway here is that the method A does not outperforms the erase and check method. It performs worse. So here are the results. We have, here on the x-axis, we have the adversarial sequence length. It's the length in token of our GCG tokens that we add for the attack. And here are the percent of harmful prompts detected. We see here at 0 added adversarial tokens that when we do not delete, or when we delete just a little bit of tokens here, 15%, 100% of the 520 adversarial prompts are detected as harmful. And as we delete more and more important tokens here, we see, for example, at 60% deletion ratio, that we have less than 20% of our prompts that are detected as harmful. This is because here we don't have any attack applied. So the most important tokens are tokens that are that make the prompt harmful. Like in the first example that we have, lethal and weapon would be the most important token in that case. And then we see that there is a decrease up until 4 tokens. This is because an adversarial attack using GCG with less than 4 tokens, in fact, we can say even 6 tokens, is not an attack that will succeed. 4 tokens are not enough to make the LLM response, or sorry, not the LLM. 4 tokens is not enough to make the safety filter change its prediction. But as we move on this axis, we see that from 8 adversarial tokens added, the attacks become to be successful and really change the prediction of our safety filter. And here we see that when the deletion ratio is relatively high, for example, 50 or 60%, it is the case where we detect most of our prompts are as harmful, because in that case, the tokens that are the most influential, that have the highest SHAP score, are the tokens that we added with the GCG method. But we don't have the same level of performance as the original paper EC. So we ask the question, what if we delete the safety filter and we directly compute SHAP on the LLM that generates the response? So before implementing or testing that hypothesis, we wanted to check which explainability method between SHAP, feature-ablation, and LIME are the most capable of detecting the tokens that were added by the GCG method. And we determine which explanation is the best at identifying the GCG suffixes. And the metric that we use is the fraction of the 20 adversarial tokens found within the top P% of the most important token. So here's the finding, our find. We see that at 0.05 or 5% of the most important tokens, we have nearly 100% of them detected as that are harmful tokens with the SHAP and feature-ablation, which are really close in terms of performance. The Lime method is way less performant, and we see as we move on this axis, for example, at 20%, 92%, between 91 and 92% of the top 20% tokens are tokens that we added with our GCG attack method. This means that the SHAP and the feature-ablation methods are effective, very effective at detecting the added adversarial tokens as the most important tokens, which means we can use them to detect and delete those tokens. So here we took a deletion percentage of 20%. Sorry, of 20%. And when we delete 0 tokens, all the responses generated are harmful because using GCG, we can trick the model into having the response, the positive response. Once we delete 5% of tokens, of the most influential tokens, we drop to 20%, which means that 80% of the response are 80% of the attacks using GCG are no longer effective and no longer works, and there is only 20% of the responses that are harmful. And as we move on, we see that the more tokens that we delete, the less and less harmful response that we get. And around 20%, we have a slight increase in the percentage of harmful responses. This is because from 20% and above, we see that the percentage of the most influential tokens that are adversarial tokens decreases. This means that we delete tokens that are not tokens of the attack, and this is why some of the responses are harmful here beyond 20% deletion. So SHAP is effective, and this is not an accident. It stems from its fundamental properties, which comes from the game theory foundation. It provides a principled fair allocation for contribution, and it is gradient aware. Unlike simple feature ablation, SHAP can leverage gradient information to understand how tokens change affect the output, making it more sensitive to see subtle manipulations of attacks like GCG. And it is model agnostic, while the implementation can be model specific for efficiency. The theory applies to any model, allowing to use on both classifiers, as we've seen in method A with the safety check, and the generators in method B. For our overall conclusions, attribution-guided defense works. It offers a massive speed up over exhaustive method like erase and check, and our method B is superior, which means applying attribution directly to the generator is more effective than using an external filter in our case. But with our work, there is some limitation. The first one is that it is a narrow threat model. The study only evaluated GCG suffixes attack. It did not evaluate prefixes attack or attacks where the tokens are dispatched in our prompt. It is a filter or model dependency. The optimal deletion ratio are dependent on the specific model being used, as we've seen. And there is an over deletion risk we might delete tokens that are not malicious tokens added by our GCG method. And this could lead to distortion in the prompt and lead to new unexpected harmful generation. Thank you for your attention.